Okay, so in class on Thursday, I think I went through this example with correlation coefficients pretty quickly. So I wanted to redo it a little bit more slowly and make sure that we cover all the most important parts of this, because I feel like there's a little bit of, we rushed through some of this stuff at the end, and not everybody quite gets what the point is with correlation coefficients. So I wanted to go through this example a little more slowly than I did. So just to remind you, we have two different tests designed to measure employee productivity and dexterity. We're going to have employee productivity being an X and dexterity being a Y. That makes sense. So we always put the independent variable on the x-axis and the dependent variable on the y. So this question that they're probably trying to test is whether or not employee productivity is tied to their dexterity, is a good predictor of their dexterity. So they grabbed several employees, randomly selected and tested with the results, and were asked to find the linear correlation coefficient R and to determine whether or not that relationship is significant at the 1% level using the critical value method. So we'll go ahead and do the null and R-standard hypotheses, and sort of follow the same set of steps that we do for the t-test and the z-test. So we got the hypotheses, we'll get the alpha value, and sort of the test statistic, t or z, we're going to calculate the value of the correlation coefficient R. So R is that number that's between negative and 1, negative 1 and 1. And then we'll figure out the coefficient of determination, that's R squared. And then instead of figuring out the critical value of t, we're going to figure out the critical value of R, and then we'll explain whether or not we can reject the null hypothesis. So before I do this, I wanted to back up a little bit and remind you what the point is of all of this. So this is a figure from your book. So what is correlation? What is R? So a correlation is always this number between negative 1 and 1. If the data have a positive slope, so if linear regression would result in an M value, or a slope of a positive number, then we'll be looking at a positive correlation. If the data have a negative slope, so if they sort of slope down like that instead, then that would be a negative correlation that we were looking at, or a negative slope. Okay, it's extremely rare to have a correlation of negative 1 or 1, because that would mean that all of the data fall perfectly on a straight line. What's more normal is to have data that are clearly related to each other. You see that X and Y are both going up together, and we can think about a line that would go through the data, but it can't touch all of the points. We can do our best job to draw a line that goes through most of the points, or that comes close to going through most of the points. And this is the whole point of linear regression, is that we found the errors between our regression line, which is the straight line, and the data points. And we tried to minimize that squared error. That's the method of least squares criterion, I think is what it was called. And that is what we used to calculate those two coefficients that allowed us to get a equation, a linear regression equation that was y hat is b naught plus b1x. Okay, and so actually all three of these lines have exactly the same linear regression equation. They are all, you see, they all have the same slope and the same y-intercept. So this line and that line and that line are exactly the same. So if you're looking at linear regression and all you see is this equation right here, you might be tempted to say that the quality of the fit that you get using linear regression for this data is the same as the quality of the fit that you get for linear regression when you do this data. And that's clearly not true. Right? These data fit that straight line much better. The statistic you were to say that is that these data are much better correlated. So we use this R value here as a way to think about the quality of our linear regression. So this is a very high quality fit. This is a pretty good quality fit. And I'd say this is a pretty weak fit, right? You can put a regression line through any data and you will get a line that has a slope. But it doesn't necessarily mean that that line that has a slope is meaningful. So when we do all of this hypothesis testing with R, which is the problem that we're doing, the test that we are doing is we are saying, okay, what is that value? How correlated are these data? How good is this linear regression line at fitting the data? And if this R value is high enough, if it's close enough to either -1 or +1, then we'll say, yeah, probably the data are correlated. But if the data are so scattered that it's really hard to actually see that linear regression is all that useful, then we will say, then we don't actually have data that are correlated enough. And we'll say that actually, yeah, sure, we can put a straight line through this data. We can use linear regression to fit this data, but statistically that line might be a line through noise. There's so much scatter in this data that regression is meaningless. So I wanted to recap that. I think we said it in the beginning, but it's sort of got kind of lost in the weeds, I think, of doing all this problem solving. Okay, so I'm going to write this down, which is that the whole point of hypothesis testing of correlation coefficients is to tell you whether or not linear regression, finding this best fit line that goes through the data, tells you anything meaningful about the data. Okay, so the reason we do hypothesis testing on R is to determine whether or not linear regression is a useful way to characterize the data. And one more thing before we go on and do this problem is, so R tells us this thing about the correlation. So it's this number that's 1 or -1 if the data are perfect, and 0 if the data are totally uncorrelated. R squared is this coefficient of determination. And the coefficient of determination tells you actually the percent of variation that you are explaining in this data through linear regression. Okay, so the R value, the R squared, the coefficient of determination of something that is a perfect correlation would be 1 squared, which is 1, which would say that 100% of the up-down motion in this scatter plot is characterized by linear regression, right? That's a perfect fit. An R value of 0.9, I'll do 0.9 squared, is 0.81. So that says that 81% of the sort of up-down motion in this scatter plot is explained by this linear regression line. An R value of 0.4 will be 0.4 squared. That's going to be 0.36 or 0.16. So 16% of the scatter here is explained by linear regression. Okay, so let's do this problem. Okay, so we need to state the null and alternate hypotheses. We need to get this data in the calculator so that we can figure out how it looks and use the calculator to calculate the correlation coefficient, and then we'll go from there. So let's state this, the null hypothesis and the alternate hypothesis. So that is our null hypothesis. That's the boring result that we are hoping to disprove. A null hypothesis is always that the data is uncorrelated. So we use a Greek letter for population data. So the population correlation, rho, the Greek R, is that is that the population correlation is 0. Our alternate hypothesis is that the correlation coefficient is not equal to 0. So it's either a negative number or a positive number. We will only do two-tailed tests for correlation coefficients. So these are always your null and alternate hypothesis. For B, the value of alpha is that we are looking for something at the 1% significance level. We're looking for 99% confidence in our result, and that is an alpha value of 0.01. And for C, what's the value of the correlation coefficient R? So I have not put this data in my calculator yet, so I guess we can do it together. We're going to go to the list and edit the list. I'll go ahead and get rid of my list from last time. If you want to get rid of a list from last time, if you scroll up so that L1 is highlighted and then push clear, clear is right here, then all the data disappears. You don't have to delete it one at a time. So that's something. So I'm going to go ahead and put all my X values in L1 and all my Y values in L2. And we'll hope that there's no typos in there. Okay, so I've got my data in here, and if you are using this calculator for the first time or you're using one of the calculators in the classroom, then we need to go ahead and turn diagnostic on. So to turn diagnostic on, you do second 0. So I'll push second and 0. And then we need to tell it to scroll down to the D's. So I find the green D, happens to be the -1 power button right here. And then it just scrolls down to the D. You could also push the down arrow all the way through everything, but probably a lot of work to do that. So I'll scroll down to diagnostic on and hit enter twice. So now I've told my calculator to calculate correlation coefficients when I do statistics. So now I'm going to go to stat, and I'm going to go over to linear regression. And I do that, and linear regression without diagnostic on would tell me the regression equation, the A and the B, which is our B0 and B1. But with diagnostic on, it's now giving me my R value and my R squared value. So I just need to copy this down. The problem says to round to 3 decimal places, so I'll go ahead and do that. And we'll get that R is 0.986. And the coefficient of determination, which is the number that says what % of the variation in the data is explained by regression, is 0.972. Okay, so this is an extremely high R value, very close to 1. These data are really well correlated. If you wanted to see a scatter plot of this, you could. Let me go ahead and copy down these regression coefficients. So actually our regression line is that y hat is 5.0549 plus 1.905 times x. I'll write that down just so that I have it. I want to plot these up just so that you can see how to make sure you remember how to do this all in your calculator. You won't need to do it in this problem, but there will be a multiple choice question or two about linear regression, so it's worth doing this through one time anyway. So what I'd like to do is make a scatter plot of the data and then also put the regression line through the data. So I'm going to go second and y equals to go to stat plot. And now I'm going to turn plot 1 on. So I'll push enter and go to there. And I see that it's actually already listed as being on, but and it's actually already listed as being a scatter plot because I have done this before. But yours might have something else highlighted, but you want to make sure on is highlighted and the thing that looks like a scatter plot is highlighted. And then we'll go over to graph and graph that. And my data shows up really nice and neat, and you see that they look very well correlated, which is consistent with this really high R value. I'm having some computer problems, so I'm going to make the rest of this go by a little quicker than I would normally, but hopefully using the pause button to get caught up if you need to kind of copy something down should work out just fine. So I showed in the previous just before I quit that I had a graph with the correlated data, and what I've added here is actually the linear regression line that I already calculated. So if I go in to my normal old y value and I write down my linear regression equation, there it is. I typed that in right there. And if I've done everything in a way that makes sense, my linear regression line should show right up on the scatter plot. I'm not going to have you do that in this problem, but I think it's a useful thing to remember how to do because you never know when you're going to get stuck on the test, and just sort of knowing how to maneuver through your calculator is probably a pretty useful thing to know how to do. So I put in the linear regression line, and now I'm going to go back to the graph, and it's going to plot that line, sure enough, right along the data, just like I expected it to. If you have any trouble seeing the data here, Zoom 9 is your friend. So if I push on the Zoom button, I can go down to 9, and Zoom 9 is the Zoom stat. It'll always, it always works for me to push Zoom 9. It always shows all of the data. Okay, so we're going to go back here. And so we had found that the correlation coefficient was this very high number, and that the coefficient of determination said that 97.2% of the data are explained by this linear regression equation. Okay, so before we go on to figure out this critical value, I want to reiterate the point of this, okay? So if we reject the null hypothesis, right, if we're able to say that the alternate hypothesis is true, that this correlation coefficient of 0.986 is statistically different from 0, that means that linear regression is a useful thing to do. It is a useful way to represent the data. Another way of saying that is that R, the correlation coefficient, is statistically significant. So these things all mean the same thing. And so we have a correlation that looks like this. Let's go and find the critical value of the correlation coefficient. So in order to use this table, this is the critical values of R table. Instead of doing n-1, which is what we usually do, we're doing n-2. So I follow this down to 8, which is the number of degrees of freedom, and I go over here to 0.7646, and that is the critical value of R that I have found. So I come over here and I say that my answer to E is that the critical value of R is 0.7646, and I put this little plus or minus here, which is to say that here's the tables. Here's the line that says what R can be, right? It can be as low as -1 or as high as +1. Any R value that is larger in magnitude than the critical value will allow us to reject the H0. So we've found an R value all the way out in here. So in this region between our critical value and 1, that's our rejection region. Those will be the statistically significant correlations. That's where ours falls. So we'll reject the null hypothesis. All the way down here, if we had instead found -0.986, we would be in this rejection region down here. It'll always look like this because we are always going to be doing a two-tailed test. Okay, so our final answer is at the 1% significance level, there is sufficient evidence to conclude that the data are correlated. So there is sufficient evidence to conclude Okay, another way of saying that is that the linear regression equation here is a meaningful or a useful way to represent the data. So I hope that clarifies some of the stuff that we've been doing with this hypothesis testing, and you should expect to see a very similar